Now that we know how to predict molecular shapes and we know about polar covalent bonds, we can combine these two concepts and predict whether or not molecules themselves are polar, which turns out to be a very important thing to be able to recognize in order to predict properties of substances based on molecules. Recall that we said that a covalent bond in which electrons are not shared equally is known as a polar covalent bond. The example we looked at back when we introduced this was hydrogen fluoride. Remember, fluorine is an extremely electronegative element, so there's a partial negative charge on one side of this molecule and a partial positive charge on the other. Partial positive charge on this side, partial negative charge on the fluorine side. So we say that there's a dipole, again pointing from the positive towards the negative, and as we'll see next quarter in Chemistry 172, once we have a negative side and a positive side, those sides can attract. There's an attraction between dipoles that leads to a lot of the properties in polar molecules. So HF has a dipole, as I've drawn in, which is just a separation of positive and negative charges. The length of the dipole vector is the magnitude of the dipole, also called the dipole moment, and is usually represented with a lowercase Greek mu, which is what I've shown here. The dipole moment is something that we can measure experimentally. Now, so far we've really just described a polar covalent bond. By a polar molecule, what we mean is a molecule that has a net dipole, where the net dipole is the net vector sum of all of the dipoles on all polar covalent bonds in the molecule. In other words, a polar molecule has one side of the molecule that has a positive charge and the other has a negative charge. Let's see some examples. If we go back to the first comparison that I had on that opening slide in Chapter 9, where I tried to motivate the idea that shapes of molecules are really important, I compared carbon dioxide with water. We now know why carbon dioxide is linear and why water is bent. So the result is, if we look at the polar covalent bonds, carbon-oxygen bonds are very polar, and this has a polar covalent bond pointed in that direction, but it also has a polar covalent bond with the exact same dipole moment pointed in exactly the opposite direction. So there is no net dipole. I add those two light blue arrows together, and you don't get an arrow. In water, on the other hand, there's a polar covalent bond pointed towards the hydrogen from this, towards the oxygen rather, from this hydrogen. There's another polar covalent bond with a dipole pointed that way. If I add those dipoles together, the net effect is a dipole that points directly in between the hydrogen-oxygen-hydrogen bond angle and straight up. That's a net dipole. That's why carbon dioxide is nonpolar and water is polar. So what we mean by polar molecules, a short and easy way of identifying them, is that polar molecules are molecules containing polar covalent bonds which are arranged asymmetrically. That is, arranged so that they don't cancel each other out. And, well, the bear doesn't have a whole lot to do with polar molecules, but he was cute, so I threw him in here. Actually, the word polar does come from the north and south pole, meaning that there's two distinct sides, a positive side and a negative side, polar opposites, if you like. So it's sort of remotely related to the usual use of polar. Let's predict whether these following molecules are polar or nonpolar. This is going to involve understanding the shape and understanding the polarity of bonds. So BrCl, there's only one bond. Chlorine is much more electronegative than bromine, so this is going to be a polar molecule. In fact, if you were to draw it, I won't draw all of the electrons, so this is not a complete Lewis structure. Nonetheless, the dipole would point from the bromine to the chlorine because the chlorine is more electronegative. SO2, if you've done enough practice and drawn these Lewis structures, this is going to be a polar molecule. And that's because it is bent. It is not a linear molecule. So if we were to draw it, it would look something like this. There's double bonds. Again, I'm not drawing a complete Lewis structure, but there's a non-bonding pair, and that causes this to be bent. The polar bonds would be pointing towards, from the sulfur towards the oxygens. Those are polar bonds. You add them together, you get a net dipole pointing down, bisecting that bond angle. This is a polar molecule. If we look at our next example, this is nonpolar. And that's because this is octahedral. So it's a completely symmetric arrangement of polar molecules. Recognizing polar molecules is really important, and you need to develop the skill to recognize them relatively quickly, because we're going to use their polarity or non-polarity to make further predictions when we go on to Chemistry 172 and look at other topics. So this is going to be a very crucial thing to be able to do. Let's do a little bit more practice. Which of the following molecules are polar? Or rather, which of the following are polar molecules? Let me read my question correctly. So we should be able to go through this relatively quickly and determine this. I'm just going to circle the ones that are polar. Ammonia, we know, is trigonal pyramidal. Nitrogen is electronegative. This is a polar molecule. HCl only contains one bond. Chlorine is very electronegative and hydrogen is not. That is a polar molecule. Calcium chloride, well, that's not even a molecule. That's an ionic compound, not a molecule at all. In order to be a polar molecule, first of all, it has to be a molecule. Carbon tetrachloride is tetrahedral in shape. That's a perfect symmetric arrangement of polar bonds. This is non-polar. Ethane, C6H12. You might think, well, I'm not sure what shape this is. It could be several different shapes. It doesn't matter, because carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar. Regardless of the shape, this is nonpolar because it contains no polar bonds. Okay. BF3, this is trigonal planar. That's a completely symmetric arrangement of polar bonds, so it's nonpolar. CH3Cl, there's only one polar bond in that molecule, so there's no way to cancel it out with any other bonds, so this is a polar molecule. Methanol, this is bent around the oxygen. Oxygen is very electronegative, so that bent bond is going to make this a polar molecule. And sodium phosphate, our last example, once again, that's not even a molecule, that's an ionic compound, so it cannot possibly be a polar molecule. Let me just show you a few of the shapes involved in some of these things and look at why they're polar. HCl, of course. This is one of our examples. There's only one bond, so it can only be polar. BF3, that was on my list. They are very polar bonds, but they're arranged symmetrically so that when you add these three vectors together, you get a net vector of 0. Carbon tetrachloride similarly has very polar bonds, but they're arranged symmetrically so that when you add these 4 three-dimensional vectors together, you get a net 0 vector. Ammonia, trigonal pyramidal, so those vectors don't cancel out. That is polar. And lastly, CH3Cl, this carbon-hydrogen bonds are non-polar. They don't contribute at all. This is the only polar bond, and that determines the polarity of the molecule.